Thank you, and thank you very much, and thank you very much also, Endre, Ted, and Gabor for being 70 years young so that we can have this very nice conference. So what I want to talk about today is a very, very specific problem. So I call a set of points, so it will be in Euclidean space, dimension D. I will call a set of points almost equidistant if for any 3 points some two are at distance 1. So of course there are many generalizations. For any k points some two are at distance 1, and there are many results about that, but I will only talk about this. So I want to look at the maximum number of points in d-dimensional Euclidean space such that for any 3 points some two are at distance 1. Okay, so I can take two simplices of unit edge length. So that's d plus 1 points and d plus 1 points, and for any 3 of them some two are at distance 1. So that's a lower bound of 2d plus 2. In dimension 2, there's a nice graph. It's famous. It's called the Moser spindle. And this graph has the property that, or this set of points in the plane has the property that for any 3, some two are at distance 1. This implies that the chromatic number of this graph is at least 4. And so the chromatic number of the plane is at least 4. This is where this graph comes from. But for us, it's important that it has this property. So it's at least 7. You can generalize this. I think then it's called the Reisky spindle. You can, in higher dimensions, instead of a triangle there, you can put a d-dimensional simplex and its reflection there, and you can make a copy of it and make sure that there's a unit distance. And in that way, you get 2d plus 3 points with this property. I don't know when this was observed first. I read it in this paper of Bezdek and Lange. And then there was another paper a bit later by Bezdek, Nasri, and Vizi, that proved that 7 is really the tight bound in dimension 2. Maybe it was known earlier, I don't know. 10 years ago, at Ted's 60th birthday conference, Iswan Talata gave a talk. He reminded me about this a few days ago, where he proved that the Moser spindle is the unique set of 7 points in the plane with this property. Okay, and he also told me that an MSc student in 2004 at Eötvös University, Bernadette Dieuray, showed that in dimension 3 the maximum is 10, and there's a unique configuration. I will show this later. I don't know what was known in dimension 4, but in dimension 5 there's this famous paper of Lahman and Rogers about the chromatic number of Euclidean space, where they give an example of 16 points in dimension 5. I will also later show how this looks like. So what about higher dimensions? So a D simplex has D plus 1 points, D plus 2 points that are all at distance 1 from each other is impossible in dimension D. So the unit distance graph does not contain kd plus 2. The complement doesn't contain a k3. That's exactly the condition. And then there's this result about this Ramsey number that gives this d squared over log d upper bound. But there are more graphs that cannot occur. So in the plane, you also don't get a k23 because 2 circles intersect in at most 2 points. And in 3 dimensions, you don't get a k33. In 4 dimensions, there's a complete tripartite graph that's impossible. Also in dimension 5, in dimension 6, there's a 4-partite one, and so on. I wrote it out like this because it's not really regular. At the beginning, it doesn't really fit. But in any case, these extra graphs don't help asymptotically, these forbidden graphs, because you can already forbid a k half d without a triangle in the complement and still get so many points. This is because there's a matching lower bound for this upper bound. So you forbid all these things already. So what was known previously is this. lower bound and an upper bound for the size of these sets. So what was known in lower dimensions? So as I've said, Istvan showed this 10 years ago, I think, in this room. But so I would just I completely forgot about this, and when I with others looked at this again, so there's Manfred Scheucher is very good with computers and computer searches and so on, and I told him about this problem, and a few, I'm sure seconds or something later, a few minutes later, he told me this. That there are two graphs on 7 vertices with no K4, no K23, and in the complement no triangle. And this is just the Moser spindle, and the other one is not embeddable in the plane as a unit distance graph. So that's it. That shows that you can also check that on 8 vertices there's just this single graph. It's the graph of the square antiprism, so it's realizable in dimension 3, but not in the plane. So this is a proof where it takes a while to write a little computer program in Sage or whatever to search for these things, but after that, modulo a little computer search, the proof is very simple. So you can do the same thing in dimension 3. So this MSc thesis of dissertation of Dury was, well, I looked at the length of the proof. It's in Hungarian, so I couldn't do much more than count pages. But there are nice pictures in there and so on. But it was a long proof. And the way how we did it was, again, there was a computer search, and then you get 4 possible graphs that you then look at by hand, and you find after, well, less than 2 pages that there's exactly one thing like that. So again, the only graph on 11 vertices with no K5, because we're in K3, no K33, and in the complement no triangle is this one. So there are these K4s, and they fit together cyclically. And so there are 11 tetrahedra. Any 2 adjacent ones have a face in common. And then if you think a little bit about it, it cannot be embeddable in R3, because there would have to be an isometry taking it to itself of order 11. So it must be a rotation. So the whole thing must be 2-dimensional, which is not possible. On 10 vertices, again, abstractly, if you look at no K5, no K3, no K3 in the complement, there are 7 such graphs. Some of them are contained in each other, so you take the minimal ones. There are 4 edge minimal ones, and of them, with this little calculation, you can see 3 of them are not embeddable. And the other one, Dan told me yesterday, I mean, I should also have looked at this, but I have difficulties reading. This is in a paper by Netschustan, where he proved that the chromatic number of space is at least 6. So this graph is realizable. I'll quickly tell you how it's done. You take a equilateral tetrahedron and you glue 2 others at 2 faces, so you get this non-convex thing. I don't know what it's really called. On Wikipedia, they say bi-augmented tetrahedron, but I don't find this term anywhere else. So I don't know. It doesn't matter. What you can do is you can put a line through those 2 horns there, those 2 tips, and rotate the whole thing. You make a new copy, and you rotate it enough so that there is a new unit distance and a new unit distance, and then this graph has this, the vertex set is an almost equidistant set. And that shows the 3-dimensional case. So what happens in 4 dimensions? Well, unfortunately, it's incomplete. So again, there's a computer search. So in dimension 4, the computer search starts taking a lot of time. So I wrote it, and it took 2 hours in Sage. Manfred Scheucher modified it, and then it took 20 minutes. But still, it's a big search. So there's only one graph on 16 vertices with no K6, no K133, and in the complement no K3, and it's not so difficult to see that it's not embeddable. On 15 vertices, the same story. There are 2 graphs, not embeddable either. On 14 vertices, there are 4 of them. You can throw one out because it contains one of the others. And these 3 graphs all contain the same subgraph on 10 points, which is not difficult to see that it's not embeddable in R4, so none of them is embeddable. So we're down to 13, and then there's a lot of graphs. Too many to really figure out whether they are embeddable or not, or at least for me. So that's the upper bound. The lower bound is like in dimension 3, and it works in any dimension. So this is just an observation we made. So maybe it shouldn't be called a theorem, but I will downgrade it to an observation as soon as somebody improves this lower bound. So what you do is, if I go back, it's exactly this construction. You start with a simplex, and you reflect a vertex in the opposite facet and another vertex in its opposite facet. And then you take some isometry fixing those 2 points. Unlike in the 3-dimensional case, it's not unique, but still you take something and you move it enough so that you create some more unit distances, and you get an example. The isometry is not unique. If you just fix 2 points in dimension 4, if you just want to fix a line, then there's a lot of rotations you can make. It's just that's not unique. But yeah. So what happens in dimension 5? So I said Larman and Rogers has an example of 16 points. So what you do is you take a 5-dimensional cube, you take all the vertices with an odd number of pluses. So if you just take the plus minus 1 vectors, they have distant square root between the ones that differ in exactly 2 coordinates. So you scale it by a factor of 1 over square root of 8. And then these, well, you get, I mean, there are 32 vertices. You get 16 components like this in the unit distance graph. I mean, 2 components, each of 16 points. You take one of them, and this is an almost equidistant set. This graph is called the Klebsch graph. Sometimes its complement is called the Klebsch graph. It's well known in the Ramsey theory if you look at small Ramsey numbers. But that's a wonderful construction, and we could use it to make some new lower bounds. I think the most striking one is in dimension 8. So you have 3 more dimensions, and it so happens that this thing lies on a sphere of radius square root of 5 over 8. And in dimension 3, a unit simplex has circumradius square root of 3 over 8. And you can put 2 unit simplices together on a sphere of radius square root of 3 over 8, so that their vertices become a vertex set of a cube. You get 8. You don't have to do that, but that's a nice way to think about it. So in dimension 3, you have these 8 points, and then in a complementary 5-dimensional space, you put this example, and then together these 16 plus 8 points give you 24 points, and they also form an almost equidistant set. And it's somehow by accident that it's because the squares of these 2 numbers add up to 1 that you get that everything works. So what about higher dimensions? So last year when I visited the Rennie Institute, there were all these people here, and they listened to this story of mine, and we thought a lot about this problem and looked at low dimensional cases and so on, and we could find this upper bound. So it improves the d squared over log d upper bound a little bit, and then a few months, well, maybe 1 month later, Polyansky showed this slightly better upper bound. This is 1.444 This was 1.5. And then after I submitted the abstract to this conference, together with Nabil Mustafa and Andrei Kupovsky, we improved this proof here, and we could bring it down to this. So, I guess I don't have a lot of time left. 4 minutes. Yes. So, yeah, as I said, the proof of this is based on this previous proof, and this proof was based on a proof that Diet gave of the following result, which I formulate as follows: that an almost equidistant set on a sphere of radius 1 over square root of 2 in d-dimensional space has at most 2D points. This is tight. So why 1 over square root of 2? Because then unit distance means you have 2 orthogonal vectors. So the result was actually formulated as, if you have a set of vectors and for any 3, some 2 are orthogonal, then you have at most 2D. Rosenfeld gave a linear algebra proof. It was very nice, but I think it was quite complicated. Diet gave an extremely simple proof. So simple that one could do something with it. So we could use it and adapt it to the analogous problem in D space. Okay, so I just want to give you a vague idea of the proof. So we take the unit distance graph. The complement doesn't have any triangle, so that means if you consider all the non-neighbors of a vertex, they form a simplex. So there's some bound on how big they can be. So you take a biggest simplex, one with the most number of vertices. Let's say k of them. And, well, so then in terms of k, you can already get an upper bound, because apart from the vertices of this simplex, any other vertex, you cannot extend the simplex. It has the biggest size. So there's always a non-edge from any V to some point in C. And the non-neighbors of any point in C form a simplex themselves. So they also have at most k non-neighbors. So you get this upper bound, which is quadratic in k. So we can assume that k is large. Otherwise, we already have the result. And then we split the set up into 2 parts. The one subset we consider is all those vertices for which the neighbors in C is a lot. So all the vertices that are joined to almost all the vertices of C. So this ugly expression here is small in terms of k. Okay, and then we first bound the complement. So the complement of this are all the vertices for which the neighbors in C is smaller than this, so that means the non-neighbors in C is larger than that expression. And then you can do some double counting argument, so you can count all the non-edges between C and the complement of this set. So you get an upper bound and a lower bound. You can put them together. So then you already get a bound for the complement in terms of this k. But of course, k is the size of the largest simplex. It's at most d plus 1 anyway. So for the complement of this set n, we already get this upper bound. And then to estimate n, we take this maximum simplex C and we just move everything so that the centroid is the origin. And now we think of the elements in n as vectors, like unit vectors. So we look at the Gramian matrix of this. And so of course this n, the number of vertices can be big, but the rank is small. But there's this very nice thing from linear algebra. It's an old result. I think at the beginning of the 20th century. So Schur knew about it. Schnirelmann knew about it. What happened? Okay. And it gives a lower bound for the rank of a matrix in terms of the square of the square of the trace divided by the square of the Frobenius norm. So in our case, what happens in our case? So there are these points, and each one of them is joined. Yeah, so just 1 minute. So each one of these points is joined to a lot of points in the simplex. So they are in the intersection of a lot of unit spheres centered at the vertices of the simplex. And if you intersect unit spheres, the intersection is also a sphere of lower dimension, a smaller radius. And if you intersect a lot of them, then you get a sphere of radius close to 1 over square root of 2. So if you have a unit, so these vectors are close to norm 1 over square root of 2. And if there's a unit distance between them, they are close to orthogonal. So we get these sort of estimates. 1 over square root of 2, almost orthogonal if there's an edge. If there's not an edge, for the sum of all these squares of the inner products, we can also get a bound. And then we can put everything together, put it into that rank lemma, and finally, when all the dust settles, we get that this set also has size at most this. Okay, and that's all I wanted to say. And so, happy birthday for the 3 birthday boys. Thank you.